Hi. In the previous video, we're looking at the common mode to differential gain. So we'll look at how to calculate that in the next part of this video. So here's a differential amplifier, and we have the input biased at VCM. We're going to be adding on to the input value V sub CMI here and here. So we're adding on an extra part to this. Is effectively the small signal part of the common mode gain. We're going to be including the effect of the output resistance, or the effect of the output resistance on the current mirror at the bottom, I sub B. What we're looking for in this is we're looking for the gain from V sub CMI, which occurs at both sides, so same gain, to the differential output voltage here. So that's our goal, is to find that gain. If we draw the small signal model for this, we have this result here for the small signal model. So we require this circuit to look like a balanced circuit. Right now there's a resistor over here which is just one resistor and not on both sides. We can change the way this circuit is drawn by just putting two resistors here. Make this 2R sub S, make this 2R sub SS, and then eliminate this resistor. Now we have a balanced circuit in the middle. So we can draw a line down the middle and see the balanced is on either side of the line. So we can take one side and draw that out as our balanced circuit. So it's equivalent to our half circuits shown here. So this is one side, this is the other side. If you notice, this has become 2R sub SS, as I discussed above. The gain for this circuit from the common mode input to the output for the left side is equal to minus RD over RS plus 2 times RSS. Again, we're doing this case for lambda equal to 0, so we don't see the finite output impedance of the transistor. Sorry. And this is also going to be the gain from VO2 to the common mode voltage. So the gain from here to there is the gain from the common mode input to this side as well. They're the same gain. So that means that our common mode to differential gain is going to be the difference between those two values, and that's going to equal 0 in this case. So the common mode to differential gain in this case is 0 because the two sides are perfectly matched. So if they're perfectly matched, there is no common mode to differential conversion. But of course that's not going to necessarily be the case. We can have a mismatch. So in the case that our resistors are mismatched by delta RD, in other words, RD1 is equal to RD, and RD2 is equal to RD plus delta RD. So we can show in this case, going through the same analysis, that when we subtract the two output voltages to look at the differential voltage, that the common mode gain, so the common mode to differential gain, is now given by this equation here. Note, by the way, that if we want to find the common mode gain, that was simply what we had up here at the top. So this was our common mode gain, but is not really of interest in this for us, but in case we want to know what that was, there it is. Now that's if we have a resistor mismatch. There's other possibilities our transistors might be mismatched. So let's say our transistor GMs are mismatched by some value. And similarly, we can show, in that case, that the gain from a common mode input to a differential output will be given by this equation here. Now, one thing about the common mode gain, so the common mode to differential gain, is we want that to be much less than our differential to differential gain. So we define something called the common mode rejection ratio. So this is the ratio of our differential gain to our common mode to differential gain. So we define our common mode rejection ratio as the magnitude of the differential gain relative to the magnitude of the common mode to differential gain. In dB form, this would be 20 log that gain. This would be in dB form. We have, from before, we found that the differential gain was this value here. So in the resistor case, we had our common mode gain was given by this value, shown here. So if we want to look at the common mode rejection ratio, we divide that 2, and we end up with our common mode rejection ratio when we have a resistor variation is given by this value here. Similarly, if we look at it for a delta GM, our common mode rejection ratio would be given by this equation here. The next thing we want to look at is the input offset of a differential pair. This will be the DC input offset. So the input offset of a differential pair, by input offset referring to the DC value of the offset, it will be the input offset voltage that we need to set the input voltage to in order that the output goes exactly to 0. So it's defined as the input offset voltage that is needed that sets the output voltage to 0. We can write an equation between that and the output offset if we define the output offset as the voltage that occurs if we set VID equal to 0. So the first part here, VOS, is what we need. It's the VID we need in order to set the output equal to 0. The second part is if we set VID equal to 0, this is what the output voltage will actually become. So it's the output offset. So if we are in the linear region, so if we assume it never leaves the linear region, which is often not going to be the case if we just zero our input, because our offset times the gain might be so large that it saturates. But assuming it doesn't saturate, then the input offset should equal the output offset divided by the differential gain. So as I mentioned, our output offset is when VID is equal to 0. So if I connect both the inputs to ground, then I measure Vout, that will be an output offset voltage, assuming it remains in the linear region and does not saturate. But that's not really practical, because if we just apply 0 to it, more often than not, the output will saturate, so we don't know what the input offset is. So the way to determine the input offset is to actually take a voltage, apply it to the input, such that the output reduces to 0. So in this case here, we actually apply minus the offset voltage in order that the output will go to 0. And then the offset is the negative of that value. So this offset, why does it occur? If everything is perfectly matched, there will be no offset. The input offset and the output offset will both be 0. But if there's mismatches in the resistor values, mismatches in the width or length of the transistors, or mismatches in the VTN, so the threshold of the transistors, then we'll get mismatch. and we'll have an input offset and an output offset. So in the case that there's a change in the threshold between the two transistors, that just appears directly as an input offset. So if we expected that if this VTN here was equal to 0.3 volts, and this VTN is equal to 0.2 volts, then we would have to adjust one of the gates by 0.1 volts such that it would effectively think the threshold was the same, and then half the current would go in either direction. So the input offset is just equal to the change in the threshold voltages. And that's what this equation here shows. And generally in most op-amps, the delta VTN dominates over the resistive mismatch and the W over L mismatch. Typical numbers for delta VTN is 1 to 10 millivolts. For delta RD, if we have an RD mismatch between the two resistors, then the input offset will equal the overdrive voltage divided by 2 times delta RD over RD. And we'll just state this and not derive it. Similarly, we'll state the result for a change in the delta W over L. And if we have a difference between the two transistors, M1 and M2, then the input offset is again related to the overdrive voltage divided by 2 times delta W over L divided by W over L. Now, so far we've been looking at fully differential amplifiers. So we've been looking at the case where we have a differential input, and that results in a differential output. So this would look something like this circuit over here, with a differential input over here and a differential output, these two. However, in many cases we want an amplifier that looks something more like this. So it would have a differential input, but a single-ended output, in this case, V out. The way to build a circuit like this is shown here. So in this case, we have a current mirror at the top that converts the current going through this path and mirrors it to this path over here. And we have a single output V out at this node. So this becomes a differential two single-ended amplifier. From a DC bias perspective, we can see that if VG1 is equal to VG2, then the current IB will split equally between the two sides, and we'll have IB over 2 here and IB over 2 through M2. This IB over 2 in M1 will go through M3 as well, assuming that M3 and M4 are matched, which they should be. They're designed to be matched. Then the current through M4 will also equal IB over 2. Since this is also, the current through M2 is also IB divided by 2, we'll have zero current nominally going in or out at the output voltage. We'd like to model this amplifier as having a Norton source equivalent model, or a current source equivalent model, where we have an input differential voltage here, a voltage controlled current source, and an output impedance R naught. So for this model, we need to determine what is GM for the above circuit and what is R naught for the above circuit. To find GM first, we can draw the small signal model as shown here. Again, we'll have a differential input applied at VID over 2 here and minus VID over 2 on the right hand side. The top node here, which was tied to VDD, is now tied to ground. And if we go through some analysis, we can show that by definition, first off, we short circuit the output here. We find I out, the short circuit output current. And by definition, GM is equal to I out, short circuit output current, divided by VID. Or I out is equal to GM times VID. If you do some analysis, you can show that GM in this case, the capital GM, is just equal to the small GM, the transconductance of M1 or M2. So GM, small GM, is just equal to GM1, which equals GM2. To find R out, it's a little more complicated. So shown here is the small signal model for it, where we apply a voltage V sub x, determine what the current I sub x is, and by definition, R out is defined to be Vx divided by Ix. With some analysis, you can show that R out is approximately just equal to RO2 in parallel with RO4. In other words, it's the equivalent of this output impedance of this transistor in parallel with the output impedance of this transistor. Now, it turns out that it seems like one simple way to explain this result is just by assuming that this node here goes to ground at the source of M1 and M2. That will give you the correct answer, but it's the wrong reasoning. In actual fact, if you go through the analysis, what you'll find is that this current I sub x has a current I that goes down through this path, but then it comes back up through this path, and then it gets mirrored through here as well. So it actually ends up that when you go through the analysis, there's a circular flow around this circuit that does give you the result of this simple result, but the simple explanation is a little oversimplified, gives you the right answer, but for the wrong reason. And these equations here go through that more detailed analysis and shows you why it ends up being given by this value here, which, as I said, is the same as if you just grounded that source, but it's a little different reasoning. So the differential gain now for the amplifier that we saw above is just going to be GM times R naught. So we have the differential gain is defined to be V out over VID. GM we found was equal to small gm, and R naught was given by RO2 in parallel with RO4. If we make the assumption that RO2 and RO4 are equal to each other, and we'll define that to be R naught, then we have the differential gain is equal to 1/2 small gm times R naught of either M1 or M4. Assuming that, and generally speaking, RO2 and RO4 may not be the same, so this might be an oversimplification in many cases. But certainly this this equation will be correct. Next, we'd like to look at a full two-stage CMOS op-amp. This is a common op-amp used within CMOS circuits, and it consists of two stages. The first stage of gain is given by here, and this is a differential to single-ended, and the second stage of gain is given by here, stage 2. And the left side, at the far left here, M8, is the bias part of the circuit. So what we have here is that we have an additional compensation capacitor that's added for stability, and we'll talk about that when we get into the feedback section of this notes. The overall gain then is going to be the gain from VID to VO1, and then the gain from VO1 to Vout. So we can write down that the overall gain is given by this equation here, A1 times A2, where we've already seen the gain of the first stage, A1, is given by minus GM1 times RO2 in parallel with RO4. And the gain of the second stage is a common source amplifier, and we've seen the analysis for that, and that's just minus GM6 times RO6 in parallel with RO7. Now, we'd like to size the transistors such that we have zero systematic offset. There's always going to be random variations between our transistors, but we don't want to design it such that it always has an offset, that even if there's no random variations, if the VTs matches, the W over Ls, there's no mismatches, it turns out we could design it to have an offset, and we don't want to do that. We'd like to design it so it has zero offset. So the random offset is still going to occur, and that could result in some 1 to 20 millivolts, but we don't want to have 10 or 20 millivolts of extra offset that's always there. We'd like the random offset to be around 0. So designed for zero systematic offset, going back to our circuit, our goal is to ensure that when we put this voltage and this voltage, so the two gate voltages equal to each other, that the current through I6 should equal nominally the current through I7. Sorry, the current through M6 should equal the drain current through M7. So we know that this current ID7 will be related to the current through M5 or ID5. So this is just a simple current mirror between M7 and M5. So we can have this relationship here, that ID7 is given by this relationship here. ID7 is W over L of transistor 7 divided by W over L of transistor 5 times IB. Our next step is to find ID6. Now ID6, at first glance, does not necessarily look like a current mirror. So we're trying to find ID6 here. But the gate to source voltage here, if the current IB at the top here is split equally IB over 2 and IB over 2 through M1 and M2, then the drain current of M4 will equal the drain current of M3. Now why do we say that? Because the gate to source of M3 and the gate to source of M4 are the same. If the drain currents are also the same, then the only difference would be if the gate to sources are the same, the drain current's the same, and the lambdas are the same, which we're assuming they all are because they're all matched, then the drain to source voltage of M4 should equal the drain to source voltage of M3. Again, if we look at the equation for a transistor, ID is equal to mu n Cox over 2, width over length, times VGS minus VT, n times 1 plus lambda VDS. If the IDs are the same, the VGSs are the same, the VTNs are the same, the width over length is the same, all of these are the same, and lambdas are the same, then the only way that this can be true is if the VDSs are also the same. So all we have left is the VDS in this equation, so they must be the same between M3 and M4. So that means that really what we have is we have a current mirror effect between here and here, because the drain to source of M4 equals the drain to source of M3, and that's hooked up like a current mirror. So that means we have an equation here now. It says that ID6 is equal to the width over length of 6 divided by the width over length of 4 times ID4. And we know that ID4 is equal to IB divided by 2, because half went one direction and half went the other direction. Half went through M2 and half went through M1. So if we go down here, we have this relationship here then for ID6. If we set this ID6 equal to ID7, so we get no offset. So we just setting these two currents equal to each other. If they're not equal to each other, one current source is trying to pull it up and it'll pull it all the way to VDD, or the other is going to try and pull it down and pull it all the way down to ground. So we set them equal to each other so they're not fighting each other. We end up then with this equation down here, and that's the relationship we need to keep true in order for there to be zero systematic offset. So let's look at this example with a differential pair. So with this example, where we have a single input VI driving a differential pair M1 and M2, and we have a current source load M3 and the output voltage Vout. M2 has gate is connected to ground, so even though it's a differential pair, we can still drive it with just one side. We don't always have to drive it with a differential signal. Our bias current is given as 50 microamps. We'll assume this value for mu n Cox, this value for mu p Cox for the p-channel transistors. Lambda prime will be given as 0.1 micrometers per volt. The threshold of all the transistors will be 0.4 volts. We'll assume that this is not matched, so W1 is twice the width of W2, and W1 is equal to 2 microns, which means that W2 is equal to 1 micron, 1 micrometer. W3 is 2 micrometers, and all our lengths are equal to 0.2 micrometers. We've chosen VB such that ID3 is nominally equal to ID2, so this will be biased correctly. We want to find the output gain from VI to Vout. So So first we need to do DC analysis, and then we can do our small signal gain. So first we note is that because of this relationship here, W1 is twice the width of W2. That means that ID1 will be twice the current for ID2. Because we're assuming first off that VI is equal to 0. So we're doing this DC analysis for the case that VI is equal to 0. So that effectively we're grounding this over here. So that means the gate to source of M1 equals the gate to source of M2. If the width of M1 is twice the width of M2, then it has twice the current of M2. So we also know that IB1 plus IB2, sorry, ID1 plus ID2, so the drain current of M1 and M2, have to sum up to be the bias current through here. That has to be 50 microamps because that's given. So that tells us what ID1 and ID2 are. They have to sum together to be 50 microamps, but ID2 has to be half of ID1. So we get this result here. ID1 is 33 microamps, and ID2 is 16.7 microamps. From that we can get the GM1 and GM2. GM1 is given by this result, which means that RS1 is 1 over GM1, which is 2.5 kilo ohms. GM2 is given by this value here, which means that RS2, which is 1 over GM2, is 5 kilo ohms. We also need to find RO1 and RO2. It's given by this equation here. We are given the length is equal to 0.2 micrometers. Lambda prime was given, and ID1 we've just calculated, so RO1 equals 60 kilo ohms, and RO2 by the same type of analysis is 120 kilo ohms. We'd also like to know what the V overdrive of 1 and 2 are. Since we know that GM is equal to 2ID divided by V overdrive, and we know the ID and the GM, we can calculate the V overdrive for both these transistors, and they end up being the same, and it's equal to 167 millivolts, which we'd expect them to be the same because the gate to source voltage is the same for two of them, and the threshold is the same. And we've scaled the currents have naturally scaled. Finally, we have RO3, which is the same equation that we had for the other ones. We know that ID3 is equal to ID2. So this current here equals that current there. So ID2 is equal to ID3. So we can draw down the small signal model now for this circuit. So it's shown here. We're going to, for finding the short circuit output current, ISC, we'll ignore R0, which is what we commonly do. If we do that, we end up with IS1 flowing down through here. IS1 is just going to be given by this voltage VI all the way to ground divided by RS1 plus RS2, which are in series. So these resistors are both in series here. So we have this relationship here that IS1 is given by this result. Now IS1 becomes minus IS2, and that becomes equal to IS1 is going in this direction, flows up through here, and then flows down through that direction. So IS1 is the same direction as ISC, and this is grounded, so RO3 does not come into play here. So we finally have that ISC is given by this result. VI divided by 7.5 kilo ohms. For our out, we can do our analysis. We have that our out, when we ground our input at the left side, we can work backwards and we can show that RI1, looking into this node, is approximately just going to be RS1. We can ignore RO1 since we're assuming GMR0 is much greater than 1. So that's about 2.5 kiloohms. And then we have that RON, given by here, is given by 1 plus GM2 R sub I1, which we just found, multiplied by RO2. That works out to be 180 kiloohms. ROP just looks like 120 kiloohms. It's just RO3. So this is ROP looking up into the drain of M3. And finally, we have that we have that R0 is just equal to ROP in parallel with RON, which works out to be 72 kiloohms in this case. So to find the gain, we have the output voltage is equal to the short circuit current times the output resistance, which is going to be ISC is VI divided by 7.5 kiloohms. The output resistance is R0, which is 72 kiloohms. If you multiply that all out, you end up with the gain of this circuit is 9.6 volts per volt and positive. So that ends this lecture, and we'll see you next time. Thanks for watching.